Log on, tune in, find out. Another good idea from Cambridge.
Okay, it's coming. So this is the last course. I will try, so in this course, to give as much ideas of the proof as possible. And since we still have only 2 lectures, well, the best I think will be that I will try to review what are, to my opinion of course, but we basically agree with Cedric, I think, on this, what are the key ideas in the proof. So that it's like a toolbox of, I hope it can be inspirative for other problems, to tell you where we have spent some time to find some new thing to solve an issue. And I will not go into the detail of all the computations. I will try to give some taste of computation at several points. So okay, just to recall, so there was a bunch of chapter, but now we have done last time, we have finished nonlinear Landau damping, result and strategy. And in this last course, we will do, as I said, some review of key ideas. So the goal is that at least you have an idea of what you could try to use, or look into the paper if you want to use a technique. So first, the 0 section is just a recall of equation and theorem. I will not give you the full statement, because if I do this it will take me 3 blackboards, but a short thing, but just to fix notation for those who were not here the last times. So we studied the Vlasov-Poisson equation in the torus in X and Rd in V. D is the dimension. The torus is supposed to have volume 1 to simplify a bit the constants. And the force F of small f is given as, that's a function of X only, it's given as a convolution by the gradient of an interaction potential. The convolution, I recall, it's a convolution in X in the torus, and it's a convolution with the density of F, where W is a function of X, and the density is the velocity average. Okay, that's the Vlasov-Poisson system in the torus. And interaction potential typically is like 1 over x plus or minus depending Coulomb or gravitation. The theorem is to say that if F0 is a stationary profile, homogeneous, and analytic, and finally satisfying Penrose stability criterion, then it is stable. It is non-linearly stable. With damping around it. Remember the damping. By damping, I mean the electric field goes to 0 and the density goes to a constant. So, let's say I try to make a list. So here are the key ideas I want to review in this course. First ideas, so each time I state the ideas, and sometimes I will try to give tasters of the computation. So the first idea is the scheme. So it's a global in time Newton scheme. Second is gliding mixed norm. So you know already what means gliding. I will explain to you what I call mixed and the associated functional inequalities. Well, this is some work you have to do. This is not a new idea, but the idea is to use this gliding norm and to mix them, as I will explain. Third is what I call finite time scattering estimate. So these estimates are meant to compare the curve characteristics with the free transport characteristics, but on a finite time. Maybe this will have time to give a proof in a baby case. Fourth point is an analytic averaging lemma theory, which to my knowledge is new. You will see what I call this averaging lemma. It has a flavor of averaging lemma, even if the form is quite different. And finite time estimate of the density. Remember, I always call density this row of F. F will be my full distribution, the distribution. 5 is regularity extortion equals and long time estimate of the density. Equals and long time estimate. So long time of rho of the density still. And the fifth section, sorry, one probably I won't have time to say a word, is a desynchronized, I don't have a better word for this, desynchronized estimate for the full distribution along the scheme. There's an additional idea, I won't have time to speak, probably, I just keep track of it here, is that all the estimates on the characteristics and all along have to be decomposed into the layers of the solution. Along, it will be clear when I write the scheme. So this is a bit arbitrary, but these are what I think the ideas which are new. I mean, there are many other ingredients which can be found in other studies. This maybe has been used in another setting, but I don't know, to do this global in-time construction of each layer of the solution. These gliding norms are reminiscent of different things. It's reminiscent of some norms used by Bourgain in the context of Schrödinger, but still it's quite different. Finite time scattering estimate, it's reminiscent of the usual scattering estimate, but usual scattering estimate is for t going to infinity, whereas here we want to control to keep track of very precise control for all time. This I've never seen before, because probably averaging lemma have not been studied in analytic setting. And also the form is quite adapted to our study. It's a good question to know. It could be useful somewhere else. And this is something also a good question to know whereas this ID could be useful elsewhere. The idea here is to take advantage of the very local in time answer of the nonlinearity, as I said already. And this improves the decay, the time decay, as compared to what you would expect. And the sixth thing is just a sort of monster. We come up. It's absolutely crucial because we would not be able to close the scheme without this. I will try to explain. But at the moment, I don't have an idea of how to transpose it to another problem. It's quite an awful stuff. Okay, so first let's start with the scheme. I will not explain again how you obtain the scheme. I just give it because we need it for reference, for later reference. So we construct the solution, remember, as Fn to be F0, the stationary solution we start with, plus H1 plus H2 plus Hn. And each layer, what I call a layer, is this. This is really the idea of a layer because it's global in time. Don't forget, each layer contributes to the final state. That's one of the funny things of this construction. And then there should be solution constructed as the first one, H1, solve the linearized Vlasov-Poisson equation around F0 with initial data given by F initial minus F0. So sorry, F initial is, I should put it here. Here I assume some initial data that I call F initial, and that will be taken not too far from F0. Okay, that's the first term. And then for any n bigger than 1, we have the following equation to solve. dth plus 1 plus v grad x h plus 1, hn plus 1, plus force created by Fn grad v h n plus 1, plus force created by hn plus 1 grad v f n equals a source term, which is minus force of hn grad v of hn. And then this is with initial data 0. So take a look at the scheme again. I will recall some things. You see that all the initial data is here. Later steps don't have any initial data. But of course, the solution is not trivially 0 because you have a source term here. Okay. And now look at what happens in this. So the first equation is exactly what we have solved already. It's exactly the linearized study. And you remember here we have this term, which means curves, that characteristics are now curves and not straight line anymore. And the force here is O of 1 in terms of n. It's not going to 0 with n. And here we have what we have already called the reaction term, where the problem is the filamentation because of this. There is a grade V, and so there is an awful growth of like T. And this is the source term which I will more or less not speak about because it's much easier than the other one. It can be controlled using the gliding norms. So important idea to recall here is that we need the stability assumption of the linearized study first, but the key thing now is that we want global in time estimate in gliding norm on Hn plus 1 if I look the equation at the bottom. And so there are several difficulties in this sentence. Even a local short time estimate is not completely for free. This is based on the Cauchy-Kovalevskaya strategy. A finite time estimate is not free at all. There is already, for a finite given time, it's already quite tricky to close a Grandval estimate in analytic norms because of the curve characteristics. And then there is the issue of going to global. Then, in order to go to a global estimate, we will take advantage that the analytic regularity can decay a bit at each step. That is crucial. The loss of regularity of the scheme comes from the passage from finite time to global in time. Remember what I mean by loss of regularity in a scheme is that my indices of analytic regularity will be a bit lower for Hn plus 1 than they were for Hn, and so on and so forth. But they will converge to something strictly positive. So in the end, it remains something. So let's go to the second idea, gliding mixed analytic norms and the functional inequalities related. So maybe let me comment, I will explain. Let me first give definitions and then comment on the choices we were led to do. So how to define some analytic norms? You have many ways to do this, but let's say canonical typical choices are either you sum the derivatives or you look in Fourier and you sum the Fourier modes with a weight. That's the two dual views about it. So let's define, to fix notation, consider some f a function of one variable at the moment, either position or velocity. At the moment, it's just an abstract definition. And we define a norm that we call big F lambda p to be f like Fourier, to be the sum of the Fourier modes k, so sorry, k in ZD if it's in dimension D. Then I assume my box has the good size. I don't want to see the size of the box. And then I put the weight in frequency times p because everything is to the power p. The Fourier mode power p and everything is power 1 over p. Okay, and this is for f periodic. In order to define the discrete sequence of Fourier modes. Second way is C like the CK space by summing the derivatives. Then I look at the entire series of the iterated derivatives. Yeah, so you should replace this with gradient if it's multidimensional. maybe let me write it like this, okay. And then I estimate in LP space. Okay, so let's look at this space a bit. In fact, for these two ways of defining analyticity, and my P, sorry, is between 1 and plus infinity. For these two ways of defining analyticity, there is each time there is a very particular P, choice of P, which is sorry, 1 here and infinite here. So f of lambda 1, which we will denote only just f lambda, because that's the most important one, is an algebra. And the same is true for C when you take infinity. Yes. And I will again denote it by just like C lambda. And then you have again this property. So this is absolutely crucial because these properties, then if you have the product, you can have the n power. If you have the powers, you can have the exponential function. And if you have the exponential function, by Taylor expansion, you're not very far away from estimates on compositions of functions. So this is the first step into some result of composition. So let me give you a hint about this. Okay, so let us give the proof. I will first give the proof of, let's take this as a proposition. And let's sketch a proof here. So maybe let me do the proof only with C lambda. F lambda is easy also easy. So you estimate sum of lambda n over n factorial of, I take this notation for compactness, it's the same as before. Yes, let's write it like a V. Okay, let's do like this, L infinity. Then I apply the Leibniz formula for the derivatives, which means I have a new sum. So now you should keep track of the sum. What do they mean? So I have a sum of m less than n. Then I have to write the binomial. And then I just use the fact that L infinity is an algebra. Okay, the product in L infinity is controlled by the L infinity of the product. And then, as usual, you note that you can cancel these two terms. And in the end, just changing the exponent n minus n to a new name, you obtain n1, n2, lambda n1 plus n2, n1 factorial, n2 factorial, and then differentiated n1 times g n2 times, which is exactly what you search for. Okay, so you see the ID, it's completely immediate. And everything is based on the fact that the underlying space here is an algebra. You can find in the original paper some amplifications of this. If this is not an infinity, you could use Cauchy-Schwarz-like inequality, and you would have similar things here, but with related coefficients, related P, Q, R, and so on and so forth. But let's stop with this level of generality. Then, let me give a sketch of what would be a composition result. Of course, I'm simplifying a lot. I'm just sketching you what is a composition result in analytic norm for this, let's say, baby norm, and then you have to assume that everything will still be provable for the much more complicated mixed gliding norm, adding a lot of indices and so on. But same result, more or less. Morally, that's the same kind of result. So now let's prove a composition type of result. So let's say, now I just denote by norm lambda either f lambda or c lambda. Because when it does not change anything to take one or the other, I just denote norm lambda. And then the proposition is the following. F composed with identity plus G in the norm lambda is less than F in the analytic norm with exponent nu, with nu to be lambda plus G norm lambda. So that's very important because this is, let's say, the typical way analytic norms are behaving for composition. You see? It is extremely nonlinear, the way it answers. If this guy becomes big, you don't pay it as usual by losing a fixed amount of regularity and a big norm in front. You pay it by losing a huge amount of regularity. That's not behaving at all like Sobolev spaces. And so then let's sketch the proof. Again, I will do the C lambda, but you could do the F lambda as well. So C lambda case, the starting point is I call H to be F composed with identity plus G. And I write a Taylor formula. So leaving aside for the moment the question of convergence of this series. In fact, of course, everything converges without problem. So everything you can be justified easily. So here I just write a Taylor expansion here in the form H of at some point x is sum over n fn at x, the point here because it's identity, over n factorial times gx to the power n. And then I have to differentiate this. Okay, this is exactly saying that I use analyticity of f. But now I want to estimate analyticity of h. So I have to apply some derivative to h. That's what I'm doing. So let's take some multi-index m. H derivated m times at x means then I have to use again a Leibniz formula. So I still have my sum n bigger than 0. And then I have a sum k plus l equals m factorial over k factorial l factorial. And I still have my n factorial here. And then I have to apply k derivative to f. and L derivative to G to the power n. Okay. Sometimes it's more convenient to write the indices, the second one between m minus k, and sometimes it's more symmetric to write it like this. You see better what's going on. And so now we sum this. So sum over m of h derivated like this. Sorry, I have to take some lambda. I want to estimate the lambda norm of h. So this is the definition of the lambda norm of h, sorry. And then I have these two sums plus a third one. So it looks awful, but in fact, everything is extremely symmetric. And you can, the goal in general here is just to repérer, to grab which indices can be just looked at completely independent. And then you want to sum out of the global sum some particular sums. Then I have my lambda here. Yes, m is equal to k plus l, so I just write it like this. This lambda is coming from here. Then I have k factorial, l factorial, n factorial. They were here. The m factorial is cancelled out by this one. I have a division by m factorial and a factor n factorial here, so it's cancelled. And I end up with and I still keep written like this the two terms of the derivatives. Okay, and then what I will do is that I will take out the sum on L. So how do I do this? I just say that this is the same as the sum over n, the sum over k, and the sum over L. As I was saying you can just see all these sums as independent because I have a sum over m. Okay, so k plus L describe m for any m means k and L describe all the integers. And if you write it like this, you can integrate out. It's a sum, but you can it's like doing this for an integral. You apply this summation here to this one, and you see that you have lambda L over L factorial. So you end up exactly with the remaining sums. So you still have n, and you still have k. And the sum over L, I will write it in detail, just means this. And then you still have the rest, lambda k over k factorial over n factorial f n plus k. Okay, L infinity. But now you recognize that this is nothing but Gn lambda. But now we can use as a black box what we just have proved before, that it's an algebra. We won't write again another sum inside, but it's an algebra. So this is less than sum over n, sum over k, g lambda to the power n, lambda k k factorial n factorial f n plus k. Now I do the inverse process, if you want, as the one I did before. I just say that these two variables could be rewritten like, if I call this big N, big N describe everything, and n plus k equals big N. It's another way to write the same sum again. And then you can see that this is exactly the binomial development of the power big N. Okay, so this means it is less than sum over big N of lambda plus g lambda to the power big N over big N factorial f differentiated big N times norm infinity. And then we have finished. This is exactly the norm of f with index lambda plus g lambda. So you're okay with this point? I just say when you expand this, you just apply the binomial rule. You get big N factorial over k factorial small n factorial. The big A factorial you cancel by this one, and you exactly end up with this. So you see, it's purely combinatorial, but you can, and then a part of the paper is devoted to amplify this for all the norms that we use. An important thing that I won't have time to prove in this lecture is that these kind of computations remain valid when you add the gliding, the time shift of the gliding norms. Everything is going through this computation very well. So to finish this section about the norms, now we should include the shift. So there are many variants. I don't want to discuss them. Oh, sorry, first. Second thing in this section, we have to see what it means mixed norm. So now now I can explain this, because you see we want to apply this kind of composition estimate when f is the distribution, and identity plus g is due to the action of characteristics. But even, to take a baby example, even if the characteristics are given by free transport, and you could imagine a small perturbation of free transport, they will still look like free transport, then G, so you see free transport means f taken at, let's say, x minus vt, for instance, vt, to get an ID. That's the change of variable due to the action of the characteristics. So G would be like this, sorry, and 0. The bad point is that on the velocity variable, we have a problem if we want to use the Fourier-based analytic norm. So first, of course, we have a problem, which is that this guy is not bounded in anything, in any Lebesgue, in anything. This is not so much a problem, because, so here I just want to say there is a problem if you want to apply an analytic norm for G. So first problem is not so big, because you can easily see that you can define homogeneous version of the norms I have introduced by removing the first term. So you can introduce f dot lambda, and also with any p is the same, is the sum for k for all frequencies different than 0. And similarly, you could define the homogeneous C lambda norm, where you remove the first order term, so let's say n strictly bigger than 0. And you could do the same with P. So these are the homogeneous spaces. So the name comes from the fact that they don't see the translation by constants, more or less. And if you use these homogeneous spaces, then at least it becomes possibly tractable, because when you differentiate, it means you start only with the first derivative, and the first derivative of v is a constant. So you end up with controlling some constant. But controlling a constant in RD means you cannot use L2 norm, and you cannot do Fourier analysis. So G in homogeneous space seems possible, but only using L infinity. And that's the reason for which on V we use the C lambda infinity, which I write just C lambda construction. Whereas on X, if we want to take advantage of the quite long detailed study we have done on the linearized equation, remember, the linearized study of Landau that we have completely cleaned up and so on, is based on studying each Fourier modes in X. So it would really be a suicide to not use the Fourier frequencies in X, because we see everything, how everything behaves for the linearized problem. So on X, we use the Fourier space. And that's why we call it mixed, because now we will have to mix the two. We mix the two recipes, let's say. I have to say that I don't claim at all that it is compulsory to do like this. You could imagine, but it's such a nightmare that we just stayed away from this. You could imagine that G, like free transport, is not L2, but the comparison of G with free transport would be L2, and you could study its continuous Fourier function and so on. But this is absolutely horrible. So in the end, we use the following norm. So to fix notation, I will give you the name that we used. We call them the Z norm. There's no reason for Z, if you wonder. I don't know where it comes from. So Z lambda mu gamma P. So be careful, I will explain all the exponents. The K is always for the Fourier modes. The N is for the derivatives. Then you have the weight in Fourier modes in X. Then we need a polynomial regularity correction, 1 plus K for gamma. Well, I just say it because it's important in the proof, but now you can forget it. It's just a technical additional problem of the norm. And lambda n over n factorial. Then the V the nth v derivative, and then Fourier mode in x only. And here you have LP, the P which is here. And this is Fourier in x only. So you see, it makes more complicated quantities to handle, but it's absolutely not difficult. I just mix the two sums. I have the partial Fourier in x, summed for all modes with a weight, and then I have all the v derivatives sum with the coefficient of the entire series. So it's just the same. And then on this, if you choose p to be infinity, you see, as compared to my construction, in Fourier this corresponds to p equals 1, what I'm doing, so the good case. And in C space, it corresponds, if I take p infinity, also to the good case. So if you do this, you have still an algebra property. It is quite expectable, even if it's more painful to write. Of course, you expect it. And you still can prove composition result. And then, last thing of this section, we shall extend this to gliding regularity. So again, the way to do this is extremely simple, but it just makes the norm even worse. And there's some comment to do about this because it's quite unconventional as a functional space to work with in PDE. So the idea is that if we have some z space, okay, with some exponent I don't want to know, then I define z with a time shift tau to be f along the pullback back the characteristics. You take the free transport characteristics backward in the starting z space. And this means what? This means exactly f at x plus v tau, sorry, v. So it just means, it's extremely simple. This just means you apply the norm written on the right to this new function. And the result is and that's the end for the norms. That's the most complicated norm I will need. Well, no, there is a part where it's still more complicated, but you don't see in the result. The statement doesn't need it. And then you still have the weight, so the weight in x doesn't see what happens, because when you take Fourier in x, it's just changing the phase to do this. So you don't see it. Which reflects the fact that the Vlasov-Poisson equation more or less preserves the x regularity. And then, remember on the right we had grad n v. Now if you apply grad n v to this, you have the usual grad n v because of this variable, but you have additionally some tau grad x. So it is just what I'm writing. But unfortunately, we have to go to Fourier, so it obscures a little bit where that this term comes from. And then here we take it in LP of dv. And that's the final norm. So where does it come from? This is just because grad v of f x plus v tau v means grad v plus tau grad x of f taken at those points. And then when you go to Fourier, you Fourier transform in x, you obtain exactly grad x gives you this, tau grad x, sorry, gives you this 2i pi tau k. And then you take the LP norms, and the change of variable when you compute the Fourier has no influence, as I said, because this is just a change of phase. So the modulus doesn't see it. So that's the norm we shall use. And again, algebra, you have algebra and composition properties. Okay. So maybe let me, I need to do 2 comments on this. First, one has to be extremely careful with this new parameter of the norms. This tau is changing, if you want, I don't have another word, the topology of this ladder of functional spaces. Because now, in fact, if I would put the lambda inside, we sum over n lambda grad x plus lambda tau grad v of f. Everybody's taken with Fourier at k, some point and a norm. Okay, and some coefficient and some exponent and so on. So it means that by playing with lambda and tau, okay, if you call these new things, I don't know, lambda 2 and lambda equals lambda 1, you have a linear combination of the 2 derivatives. And this is like going in terms, you know what, that when you go from R to R2, you lose an extremely important thing, which is the order, the total order of R. And then you cannot compare things anymore. You can turn around and so on and so forth. This is the reason for which systems of equations are much, much harder to handle than scalar equations. For instance, in hyperbolic systems, when you lose the order, it's a mess. But here, you lose the order on the exponents of your functional spaces. So what I mean is that if I give you z lambda mu gamma, so gamma we don't care so much, and z lambda prime tau prime mu gamma p, these 2 spaces are extremely hard to compare in general for lambda prime tau prime. In general, it is impossible to compare. Okay, just like you cannot compare 2 points in R2. But, so the conclusion of this is that we will, all along the proof, it's extremely important that the tau stay always close to the same value for all the functions we estimate. We cannot play too much with the tau. The tau has to follow free transport. If you modify tau a lot, you pay it by an enormous loss of your other exponent. Okay, that's the first remark. And second remark is that now the extremely nice aspect of this norm is that if you project the norm on functions depending only on v and only on x, they just become again usual analytic norms, and they give you what you search in terms of damping in x. So if f depends only on v, then f in the norm z lambda mu p tau, sorry, just becomes f c lambda. So you forget the shift and everything. Second, if f depends only on x, and that will be the case when we will apply this kind of norm to the force field and so on, then so let's forget the gamma for a while. It means you obtain f in the Fourier-based analytic space with exponent lambda tau plus mu. In fact, there is an absolute value. So which means you immediately see here you have an increase of regularity, which is exactly the thing we had observed before. You remember when we were asking about this gliding regularity estimate, the decay in Fourier frequencies in X was improving with time. And that is exactly optimally included in this kind of in this way of writing things. When tau is increasing, apart from the zero mode, which does not move, everything will go to zero because of this estimate. So this is something we will use a lot, and a very nice feature is that even if you estimate something along characteristics and so on and so forth, you can use all the composition result. If at the end of the composition something depends only on x, we shall be able to take advantage of this to get some decay. We can propagate by composition or these awful unordered norms, and if in the end something depends only on one of the two variables, then we get again some order on the spaces. That is the key idea of these spaces. So maybe before the break, I'm just telling what I will do after. So third idea is about the scattering estimates. Finite time scattering estimates. The goal here is to compare free transport and the curve characteristics. And I just stop on this. Remember, I will write each time which part of the equation we want to tackle here. Here the goal of this part is to handle I put everything on the right, which I don't want to know at the moment. The goal of this idea is to handle this curved characteristics because of this force. So let's call this S, and since the force is non-autonomous, I have to precise that it's from time t to another time tau. It does not have a group property on the time because the force is not time independent, which means, sorry, let me write it here in detail, big X of t tau, big V of t tau. And if needed, I will skip I will not write the index when it's not needed. If needed, I just keep track of the fact that it depends on the force created by the function at the nth step. And this I want to compare with the free. Okay, I'm not sure it is compatible, the notations, but well, 0 is n equals 0 would also mean free transport characteristic, by the way, so it's fortunate. But here I just mean the free dynamics. So here is just taken at xv. It just means x minus t minus tau v. And we want to compare this, but for every time. And a first nice bootstrap that I will be able to give you a proof in a baby case. A first nice bootstrap is that if the force satisfies this damping here, then we will be able to say that this is close to this in the Z norm. So if the norm is damped, if the force is damped in the sense that it satisfies this kind of thing, which is exactly the projection of the Z norm when you depend only on X, so that's absolutely coherent from the force field. So if the force field satisfies this, then we will be able to compare this composed with inverse of this to stay uniformly bounded, and you see it's even better, in fact, in some sense, in the Z spaces. So there is a bootstrap. The gliding space are also good spaces for controlling the discrepancies between the curve characteristics and the free transport characteristics. Okay, so maybe let's do a break now.
You can close this sort of features.